So this is part 3 of Work Power and Simple Machines, where we start going into simple machines and what they are and what's going on. So this might get a little confusing, so let's get started. Feel free to pause me whenever you need to. Alright, so first of all, the question is, well, what is a machine? And the first, or at least the way we think about it in physics, is that it's a device that multiplies forces or changes the direction of a force. Okay, so if you exert a force into this machine and then it makes something else, let's call it let's say a wrench. Okay, you can't twist. Let's say you get to a point where you can't twist the nut off of a screw. So what do? You use a wrench. It gives you some leverage, and it allows you to push with a force, which then makes the force bigger down by the nut. Okay, the point is you use the machine to get a bigger force. Okay, the idea is then also, some people say it makes work, quote, easier. It depends on what you mean by easy. If you're talking about how much work you actually technically do, no, they don't actually make it easier. But if you talk about the force that you need to apply, well, yeah, it does make it easier, because the machine makes it so that you use less force and the machine multiplies that force. However, you'll find out soon that the work stays the same, but we'll talk about that later. Now, there's a difference between a machine and a simple machine. Now, a simple machine does this multiplying of forces. It does it with one simple motion. That's what a simple machine does. And the thing is that you can take many simple machines, let's say a lever, an inclined plane, or a wheel and axle, or a pulley. You can combine those together to make what's called compound machines. Okay, that's really about it as far as what a machine is. So now let's get into some of the more interesting parts. Okay, so what does a machine actually do? Well, I already stated it multiplies your force, right? So let me explain this with an example. Okay, this is a lever. Okay, you've got the fulcrum here, okay, and you've got the the lever here. Okay, let's say there's a big heavy rock, okay, on the one end, and you're trying to lift that rock, but you can't just lift it up. You want to get some leverage. You want to get something to help you out. Okay, now let's say the biggest force that you can apply, let's say, is, I don't know, 80 newtons. Okay, so what you're going to do is you're going to apply 80 newtons of force. Okay, so you're going to apply 80 newtons of force. Okay, sometimes we actually call that, instead of the applied force, sometimes we call that the effort force. Okay, so you're going to apply 80 newtons of an effort force. Okay, that's what you can apply. And along with that, okay, let's take a look at this. This lever, just by happenstance, it happens to be about twice as long on this side as it is on this side. About twice as long. So what's going to happen, okay, is when you actually push that down, it's going to move a distance. Okay, and let's just say, I mean, this is kind of wild, but let's just say it moves a distance of 2 meters. Okay, that will make the math come out easier. Trust me. Okay, so it'll move a distance of 2 meters. Now, here's the thing: the way this lever works, okay, because it's 2 times as long on one side as it is the other. Okay, what's going to happen is your force going up is going to be twice as big. So now the force coming out is going to be 160 newtons, which is good because you couldn't do that before. You couldn't lift it. Okay, let's say it's 160 newton rock. You needed to exert. You could only give 80 newtons down, and then because of the simple machine, it multiplied that to give you 160 newtons. Here's the caveat, though. The trade-off. Okay, the trade-off is that after you lifted it, okay, here's the same rock. I know it looks different, but it's the same rock. It only went up 1 meter. Okay? So what you wind up getting is your forces are multiplied. Okay? Notice it went from 80 to 160. In fact, it's multiplied by 2, but the distance got cut in half. So the machine multiplies your force, but here's the key part, is that it's at the expense of distance. Another way of saying it is that this lever in particular multiplied your force by 2, but made the rock lift up only half as high. So it multiplied your force by 2, but it divided your distance by 2. Divided your distance by 2. Okay? Another way of looking at this, let's take a look. Let's look with another pen color. Okay? Oh, by the way, this is known as the resistance force. Okay? The force that you get out. Okay? Sometimes we'll call it the force out, whereas this could be called the force in. And over here, this distance, this could be known as the effort distance, because that's the distance that your effort force moved, or some people call it the input distance. This would then be, obviously, the resistance distance or the output distance. Okay? Just to keep those things in mind. All right? Your inputs are your efforts, your outputs are your resistance. Okay. Like I said, another way to put it, okay, if you look at the work that you put into this machine, okay, the work that you put in, you exerted a force, okay, we'll call it the input force, over a distance, we'll call it the input distance, okay? So the work on this side is whatever your effort force was, which was 80 newtons, okay, let's do 80 newtons, times whatever the distance was that this moved, which, as we saw over here, was 2 meters. So you did 80 newtons over 2 meters. That gave you 160 joules of work that you put into the machine. What you get out, well, remember we said that the force coming up, the resistance force or the output force, was 160 newtons, right? But the distance was 1 meter. So if you do the work over here, the output work is the force times the distance over there. You got 160 newtons times 1 meter. And that, of course, is 160 joules. So the work that you got out is equal to the work that you got in. So the key here, let's move on to the next slide, is that the work that you put in, will always equal the work that you get out. Now, this is under ideal frictionless conditions, which we're going to assume because this is physics class and it's easier to do it that way, especially in 9th grade. However, that's the idea. The work you put in is the work that you get out. All right? So you had to put a certain amount of work into this by exerting a force over a distance. Okay? You put that work in, okay? Distance and a force, okay? And what you got out, the work out, oops, I made that blue. Oh well. The work out was the force that was exerted up, okay? And the distance times the distance that it traveled. In fact, this force should probably be twice as big, okay, as this force, okay? Now that's in this type of lever. If this lever was super, super long, you would actually get much bigger forces and much smaller distances, but that's not the point, okay? The point is, the work that you get in, this is an essential equation. Pause me, write it down, okay? The work that you put in equals the work that you get out, all the time under ideal conditions. Now what that means is, remember there's an equation for each one, okay? Like the work in equals, what do we say? The force, the input force times the input distance, and the work out was the output force times the output distance, okay? So what you get is finned in equals fout out, otherwise known as input force times the input distance equals the output force times the output distance. It's just FD, just focusing on the inputs equaling the outputs. Okay? And lastly, another way of putting it, this is the only thing, is that the input, like we said, is also known as effort. Okay, so when we talk about input, anything that's an input, that's also known, I'll do the squiggly ones there, as an effort. Okay, that's these guys. This is your effort force. That's what you put in. Your effort distance, that's how far you push it. Over here, your outputs are known as resistance. Okay, so this is the resistance force and the resistance distance. That's how much the resistance moved and how much force you got out of that. Okay. All right, so just remember, these equations, whatever work you put in is the work you get out. So the work stays the same, okay, but the force can go up or down, and the distance therefore goes down or up. Remember, now the force and the distance are inversely proportional. Okay, so if it multiplies your force, it's going to reduce the distance that it moves. Okay, that's it for simple machines. Write down any questions that you have, and I'll see you in class.